In the 1800s, paddle wheelers plied these waterways. They were driven by steam that comes from water. Now, water, along with the sun, is probably one of the most influential factors in the history of civilization. If you take a look at this map, you can see a lot of water. Oceans, lakes, rivers. Water makes up some of the most important features. And look at this. Every major city or town is located next to a body of water. There's an important relationship between water, power, and people. And it's simply science. Paper, magnifying glass, sunlight. And can you predict what's going to happen here? Sure enough, the lens of the magnifying glass concentrates the energy of the sun, causing a temperature change in the paper. It's a way of harnessing the solar energy to perform useful work. The sun contains huge amounts of energy. Now imagine if we could capture just a small portion of it and put it to work. Well, in fact, we do just that every day, and in a variety of ways that may just surprise you. Energy. We can't see it, but we know it's all around us. And that's because we identify energy by the changes it causes. We can transfer energy into a system and give it motion. We can transfer energy into a system and cause the temperature to go up. And if we take energy out of a system, the temperature goes down.
Producers are organisms that absorb solar energy and then convert it to food. Consumers eat other organisms to acquire the energy they need.
Can you explain the connection between plants and oil and gas?
Yes, in the early oceans that used to exist here 350, 400 million years ago, there was animals and marine animals and plants growing in that atmosphere. And through the process of photosynthesis from the sun, the plants over the many years turned into products that developed later into carbons and hydrocarbon products.
Are there different types of oil and gas formed from different organic matter?
Yes, they are, and from the different organic matter and also the type of environment that organic matter is either grown in or trapped in. The silts come in and the caprock comes in, and it creates the different types of crude oil.
Why is there so much oil and gas found in this area?
Well, Alberta was blessed with having a type of source rock many millions of years ago in the oceans and the silts and the making up the source rock. And this trapped a lot of hydrocarbons, and we've been able now to trace that source rock and then find a lot of hydrocarbons throughout Alberta.
So then it's the refining process that turns fossil fuels back into reusable energy?
Yes, that's correct. When we produce oil out of a whale, it's called crude oil. It's an oil with a whole bunch of products in it. They're unusable in that present form. Once they go through the refining process, it's distilled down, and the lighter products come off the top and the heavier products come off the bottom for use for you and I in domestic situations.
Energy is the ability to do work, the ability to apply a force over a distance. The horses pull the wagon over a distance. They transfer energy to the wagon. They do work on it.
This is work.
So's this.
This isn't.
This is.
Not this.
Not for me, but the horses are working.
Work means force through a distance. It doesn't matter how much effort you expend. If it doesn't move, there's no work being done.
So what is crude oil?
Crude oil is raw, unprocessed petroleum, which is a mixture of gaseous, liquid, and solid hydrocarbons comprised mainly of the elements carbon and hydrogen. The chemical and physical properties of crude oil vary significantly and can be termed light or heavy depending on their density and viscosity. In Alberta, we're fortunate to have both conventional and non-conventional reserves. Petroleum derived from oil sands is more correctly referred to as bitumen. It is mined, extracted, and upgraded into synthetic crude oil. This crude oil supplies about 20% of Canada's needs currently, and in 25 years may supply as much as 50% of Canada's needs.
So how do you get energy out of crude oil?
In its crude state, petroleum has minimal value. We have to add energy in to get energy out.
Energy in what form?
Energy in the form of refining, which is a series of processes where the crude oil is converted by chemical and physical means into something more useful. It must be heated by combustion and steam so that it cracks, fractionates, and essentially distills. This is because hydrocarbons are configured differently. Hydrocarbons like paraffins, naphthenes, and aromatics.
When we add thermal energy to a system, whether it's crude oil or hot chocolate, we increase the kinetic energy of the molecules. Molecules on the move. That's what you get when water boils. When work is done, or when plants grow. And on a global scale, molecules are on the move because of the sun. The hydrologic cycle, prevailing winds, ocean currents. They're all driven by solar energy. In fact, solar energy is absorbed by the biosphere and converted into virtually every form of energy we use.
Can crude oil be converted into other types of energy?
Yes, by adding heat and chemical energy. In catalytic cracking, for example, we take high boiling point fractions and fractionate them into lower boiling point fractions. In hydroprocessing, we take the feedstock and treat it with hydrogen at high temperature and pressure using a catalyst to remove components like sulfur and nitrogen.
What do you mean by fraction?
A fraction is any portion of a mixture that has closely similar properties. This is an example of oil sands and the extracted crude oil or bitumen, and these are fractions of similar boiling points. Important streams in a refinery include gases, kerosenes, gas oils, and residuums.
What kind of products do you make from these fractions?
The dominant use of petroleum products is as a source of energy. Over 85% of crude oil is used as a fuel in the form of gasoline, diesel, aviation fuel, or home heating oils, or gas oils for electrical power generation. Other materials include lubricants, asphalts, solvents, and petrochemicals for polymer production.
When it comes right down to it, almost all the energy we use can be traced back to the sun. And with all its different forms, finding new ways of harnessing energy to perform work has become one of society's great passions. For centuries, people have used water for transport. It may have just started one day when somebody looked down in the river and saw a log and thought, hey, maybe I'll just tag along for a ride. Eventually, rafts, dugouts, and other primitive boats were developed. And then one day, somebody made a major discovery. By rigging the world's first sail, a brilliant sailor harnessed the kinetic energy of the wind.
In order to detect the wind direction, what clues can we look for?
There are many indicators of wind direction all around us, including wave action, perhaps some smoke from a chimney. We can look at flags. There are indicators at the top of the mast. Or you could simply wet your finger, hold it up in the air, and decide which direction the wind's coming from.
Wind. It's a good example of kinetic energy, air molecules in motion.
Solar energy is absorbed by the Earth's surface. The heated surface then radiates energy back to the air molecules, creating convection currents.
These convection currents combine with the Coriolis effect of the Earth to create the prevailing winds.
Right now, we're positioning the sail to take full advantage of the wind.
That's right. We set the sails using the telltales, or strings that are attached to the sail. When all of the telltales are flying straight back, it shows a lack of turbulence along the surface of the sail. The foresail, or jib, has telltales on both sides of the sail. When all of the telltales are flying straight back, we're getting all of the power from the wind that we can.
For centuries, people have harnessed the energy of the wind using windmills.
principle is pretty simple, really. The molecules of air in the wind hit the sails of the windmill. The energy of the wind is transferred to the sails, causing them to rotate.
Inside the windmill, energy is transferred to the millstone. Grain is fed into the millstone, where the kernels are ground into flour.
Windmills were originally used for milling grain, but they are also a common mechanism for pumping water.
And now they're used to generate electricity.
Where the sun's energy creates convection currents which result in dependable winds, an investment in windmill-operated generators makes sense. These high-tech descendants of windmills still operate on the original principle. The air molecules of the prevailing winds collide with the surface of the windmill blades. The kinetic energy of the air is transferred to the blades, causing them to spin. The motion of the blades turns a turbine, which generates electricity.
This is an anemometer, a wind speed indicator. How does it work?
Well, as the air travels, the molecules collide with the cup, transferring kinetic energy from the molecule to this device, causing it to spin. The faster the wind, the faster the spin. We can determine the exact velocity by measuring how far it has traveled and timing how long it has taken to travel.
So from a work-saving device like a simple sail to the high-tech design of electrical generators, wind power provides an inexpensive source of energy that doesn't pollute the environment. Unfortunately, it isn't all that dependable. When there's no wind, there's no power. Throughout history, rivers provided an easy form of transportation, and they also turned out to be a reliable power source. Wherever there was a flowing stream, water wheels ground grain, sawed wood, and operated production machinery. The water, harnessed by the water wheel, turned out to be the single most important source of power until the coming of steam.
Water wheels take advantage of two important phenomena in nature: the water cycle and gravity.
First, the water cycle. The sun heats the water in oceans and lakes, causing it to evaporate.
The water vapor stays in the air for a while, until conditions are right.
Finally, clouds form. Then the water falls back to the earth as precipitation.
Which does involve gravity, but there's a bigger role for that force.
Water flows downhill. That's what gives it its ability to do work.
Right. Water wants to reach the lowest level, the ocean. If it has to move a few obstacles to get there, it will.
Even if the obstacle is an artificial one, like this water wheel.
The water molecules hit the paddles of the wheel. Some of the kinetic energy of the water is transferred to the wheel.
As the wheel turns, its energy is transferred by a shaft to the machinery inside the mill.
That's just how a hydroelectric plant works. Work done on the water to lift it above the dam is stored as gravitational potential energy. When that water flows down a pipe called a penstock, the gravitational potential energy of the water is converted to kinetic energy. At the bottom of the pipe, there's a turbine, a specially designed high-tech water wheel. And when the water hits the blades of the turbine, the kinetic energy of the water is converted into the kinetic energy of the turbine. And that's transferred to the kinetic energy of the generator, which is converted to electrical energy. So one of the oldest technologies, the water wheel, allows us to convert the sun's energy through the hydrologic cycle into electrical energy. For centuries, the only way to travel was to use wind or muscle power. You could walk, row, ride, sail, or float. And aside from a few improvements in the design and making of carriages and wagons, centuries went by with few changes to travel technology. And that is until somebody figured out how to combine the energy of the sun with the power of water.
Right now we're standing in the locomotive shop at Fort Edmonton Park. This is where the restoration project on the steam locomotive is being carried out. Right now you're looking at the chassis of a 1919 Baldwin steam locomotive. The boiler is a round vessel which normally sits on the top of the chassis. It's at a repair facility in town being rebuilt. After 77 years of use, it needs a good rebuild. The vast majority of steam locomotives at that time burnt coal. It was cheap, readily available. They could store it alongside the track and replenish the supply as they needed it. A lot of other locomotives, light locomotives that were used on branch lines, they burnt wood because, again, that was cheap and everywhere and abundant. Those were the two main sources of fuel. In the later years, they started burning oil.
So what have we got here?
A lump of coal.
Which is actually dead plant matter compressed over thousands of years.
When the coal burns, it gives off thermal energy. Do you know where that thermal energy comes from?
Well, if the coal was plant material at some time, then any stored energy it has must have come from the plants.
Which means before that, it must have come from the sun.
So in other words, when you burn coal, you're releasing chemical potential energy that originated from the sun.
From thousands of years ago.
Ancient sunlight. Cool.
The fire on this little model here is driven by alcohol. You can see the flame down here. The top section, this round section, is called the boiler. The water is filled inside this boiler to this level. Above that, the steam is collected. The steam goes through this valve here, through this tube, and into the steam chest of the engine. There's a valve inside here moving up and down which directs the flow of the steam to the top or the bottom of the cylinder. It's the pressure of that steam inside that cylinder acting on the piston that moves the piston up and down, connected to the flywheel, and that's what's turning the engine.
So what happens when you add thermal energy to water?
Well, if you add enough thermal energy, it transforms the water from a liquid to a gas, water vapor.
Why is that?
Because when you add energy to a system, the molecules gain energy.
What happens with water molecules is they get so excited they need more room between them.
Well, here's a model steam engine. What do you think will happen when we inject steam into this tube?
The pressure from the steam will push the pistons out.
Sounds reasonable.
Once the steam's created, it's collected in the top of the boiler here. It's then transmitted through a series of pipes into the steam chest. This is a valve that's located above the cylinder. The steam then goes inside the cylinder and pushes against the piston. The piston then transmits this power through these series of rods, and that's what turns the wheels. Just like a kettle on a stove, as it boils, the water will disappear. The water has to be replaced inside the boiler at constant intervals, but the supply of that water is in the form of a car that's towed behind the engine called a tender. Now the train will come up to replenish its water to a water tower. The water tower is a big tank that's along the track, and it's filled up by a windmill which pumps the water into a tank. When the train pulls up and stops, the spout will come down, and that will fill the tender up. The water is forced by gravity from the tank into the tender behind the train.
So how does a steam engine work?
Well, the expanding water vapor pushes the pistons out of the cylinders, like this.
So the water vapor exerts a force on the piston and moves it through a distance.
Which means work.
Right. The steam does work on the piston.
60 seconds of silence.
The first steam engines were stationary affairs, used to replace water power in the operation of mills. But before long, the new contraption had been mounted on wheels, and the railroad was born. Although steam engines did need water for their boilers, the development of railroads changed the pattern of travel and the movement of goods. Steam turbines at sea meant that ships were no longer at the whim of prevailing winds. Railroads have replaced steam engines with electric and diesel-electric engines, but steam power still has its uses. Steam turbines are a common power plant aboard most ocean-going vessels, and steam turbines generate most of the world's electricity.
Can you explain how a coal-fired generating station works?
Well, basically, it converts the chemical potential energy stored in coal into thermal energy.
So thermal energy is transferred to water, which is converted to steam. And the steam drives the turbine, which in turn drives the generator.
That's right. And the kinetic energy of the generator is converted into electricity.
The relentless force of steam expanding out of boilers replaced the muscle power of people and animals. It was the steam engine that first gave people the notion that we could release thermal energy and convert it into mechanical energy. It's a notion that shaped the 20th century.
Work is a transfer of energy. Whenever energy is transferred from one system or object to another, work is done.
Okay, so work is done when force is applied over a distance.
And we can calculate how much by multiplying force times distance.
Right. W equals F times D. And the units?
Well, force is measured in newtons, and distance is measured in meters. So work is measured in Newton meters.
And a Newton meter is the same as a joule.
Well, isn't a joule also a unit of energy?
Well, that makes sense. If it takes energy to do work, then the amount of work done should equal the amount of energy required.
So then work and energy are equivalent.
That's right. Work done equals energy transferred.
Whether you're in the middle of an ocean or in the middle of a large lake, it may be impossible to see landmarks to help you determine where you are. And even if you're close to shore, there are hidden obstacles, such as rocks, reefs, or sandbars that can make sailing hazardous. Sailors rely on a number of navigational tools, such as GPS or Global Positioning System, LORAN, or charts such as this one. We can work from a chart to determine where we are if we can see the landmarks. For example, there are 3 stacks across the lake from us. If we take a bearing between ourselves and those 3 stacks, 190 degrees, we mark that on the chart, find another landmark, and where those 2 lines cross, it determines our location.
If you've ever had the chance to crew on a sailboat, you can appreciate the amount of effort it takes just to sail a short distance, let alone around the world. In science, we have a simple way to visualize and interpret common information. This graph represents the energy change required to change the position of the sailboat. The y-axis represents force, and the x-axis, distance traveled. Suppose we have a constant breeze that provides 500 newtons of force to the sails. If the skipper keeps the boat on a constant straight course after, let's say, 20 meters, the graph looks like this. So how much work was done on the sailboat?
Well, work equals force times distance. And in this case, 500 newtons times 20 meters, or 10,000 Newton meters.
But check out the graph.
Okay, if we multiply force times distance, that's the same as multiplying the amount of x by the amount of y.
Good. Now if we think of this as a rectangle, multiplying the x value by the y value is the same as multiplying length times width. And length times width is area.
So the area under the curve would be 500 newtons times 20 meters. And that gives us 10,000 Newton meters.
In other words, if the x-axis represents distance and the y-axis represents force, then the area under the curve equals the work done. And that's a lot of work.
And it's all done by the wind.
Yo, that's rap.
Energy is the ability to do work, and the world is full of natural examples of energy transfers. Throughout history, people have come up with a variety of methods to put those transfers to work, literally. From wind and water power to the release of energy we get from burning fossil fuels, we designed a whole range of technologies to harness energy. But in the end, we're just taking advantage of energy from the sun. It's simply science.